Good afternoon. Today's lecture is on remote sensing study for extreme events. In this lecture, first of all, we will cover the definition of extreme weather events. Then we will see the statistical distribution and how to define an extreme event if you are given the data set. After that, we will see some satellite images. If you are given satellite images corresponding to visible channel, infrared channel, and water vapor channel, how you can use that particular information to describe certain weather phenomena. And after that, I'll discuss about some studies which are based on the rain gauge measurements and also the other available data sets. So extreme weather includes unusual, severe or unseasonal weather or the weather conditions at the extremes of the historical distribution. The most commonly used definition of extreme weather is based on an event's climatological distribution. Climatological distribution means if you are given a data set of one particular place about some parameter, suppose you are given a data set of temperature, surface temperature, and you have data set of 50 years time period. And if you are asked to plot the distribution, then the extreme events will be those events which are lying at the tail of this particular distribution. This tail could be in either side, either the positive side or the negative side. And extreme weather occurs only 5% or less of the time. According to climate scientists and meteorological researchers, extreme weather events have been rare, or in other words, extreme events are the rarest events. So as I said, if you are given a data set and you plot the histogram, based on that histogram you can define what kind of events were at the tail and what is the limit of those particular events. So this is just the schematic, this is not the actual distribution of a parameter. Just to give you an illustration, I have plotted this curve. Histogram gives you information about the number of events corresponding to certain limits or certain values on the x-axis. Suppose I plot temperature here, then curve may not be like this. You may have some values on the left side also. And if I plot this curve for rainfall, and the unit of rainfall will be either millimeter per day or millimeter, it could be centimeter also. So that curve may be in this form. And if you are given the data set of velocity, then the unit of the velocity will be meter per second, and you can have again this kind of curve. So this curve shows us that number of events on the y-axis and the different limits or the values of the rainfall or the temperature on the x-axis. What do you see here? There are more number of events corresponding to lesser values, and as you go up towards the higher value side, your number of events are decreasing. And as per the definition, we just have seen in the first slide that the extreme weather occur only 5% or less of the time. So these events are the rare to the rarest. So as expected, the extreme events would occur at the tail of this particular distribution. So depending upon this curve and this particular limit, we can have a threshold and we can say that this particular event may be considered as an extreme event. Extreme weather events are mainly responsible for extreme temperature highs like heat waves, storms including windstorms, tropical cyclones, etc. High level of precipitation and associated flooding is also a form of extreme event, and lack of precipitation and associated drought. It means I'm not just talking about the values at the higher end, even you can have values on the other end as well. Suppose we are in a place where the climatological distribution of temperature says that at most of the time the surface temperature is of the order of 20 degree. But for instance, and for a particular day, you have some surface temperature of the order of -5 degree. So that particular event can be considered as an extreme event. And for the same place, if you have temperature, surface temperature of the order of 50 degree, that also may be considered as an extreme event, because the climatological distribution says that on an average, the surface temperature should be of the order of 20 degree for this particular place. So that is how we use the statistical distribution of the climatological data set to decide which event can be considered as an extreme event. Cyclonic storm may also be considered as an extreme event, and this is that which forms over the oceans. It is caused by evaporated water that comes off the ocean and becomes a storm. The Coriolis effect causes the storm to spin, and the hurricane is declared when this spinning mass of storms attain a wind speed greater than 74 miles per hour. It's about 119 km per hour. Hurricane is used for these phenomena in the Atlantic and Eastern Pacific Oceans, tropical cyclone in the Indian Ocean and Bay of Bengal. Typhoon is the name for this particular storm in the Western Pacific Ocean. If we just look at this time series of the formation of the cyclonic storms, we would see that in the Bay of Bengal, the most number of cyclonic storms occur either in the pre-monsoon season or in the post-monsoon season. So these conditions are actually favorable for the formation of cyclonic storms. And for the monitoring of these kind of extreme events, the remote sensing techniques are being used, and one of them is the VHRR images, very high resolution radiometer images. If you are given the sequential images from VHRR, you can actually monitor the progression of cyclonic storm in any of the ocean. Likewise, if you are having a less amount of rainfall that is considered as an extreme, but on the other hand, the less amount of the precipitation is also considered as an extreme, and the amount of, as per the IPCC report, Intergovernmental Panel on Climate Change, it's suggesting that in the coming years the amount of drought may be increasing. So this is also one of the form of the extreme event that is going to be increasing, and the reason is higher temperatures lead to a high rate of evaporation and very dry conditions in some areas of the world. Researchers are not sure if drought has increased as a result of current warming or it's a part of the long-term climate change of the globe. And also we just look at the snow cover. The summer thickness of Arctic icebergs is about half of what it was 50 years ago. This melting ice may someday cause changes in the ocean currents. So this is the satellite imagery which was developed, and this particular figure is for September 1979, and this particular pictorial representation is for September 2007. What we do see here in this picture that the ice cover is actually decreasing over this time period, and it's long been known that melting Arctic ice could help speed global warming. As the ice melts, surface reflectivity changes, more heat is absorbed than reflected, and as a consequence, more warming. This particular study has been reported, and this could be downloaded from this given web link. And since 1989, the Arctic has warmed over 2 degrees centigrade. The measurement shows that, compared to a global average of 0.5 degrees. So it's getting very rapidly as compared to the other global distribution of the temperatures. Now we will just see the usage of satellite imageries to understand the weather phenomena. To monitor the weather phenomena, the geostationary meteorological satellites are being used, and this particular schematic shows the position of Indian geostationary meteorological satellite. INSAT 3D is not being shown in this figure, but the data from INSAT 3D is also available. Here we have shown the Kalpana 1, INSAT 2E and INSAT 3A. INSAT 3A Kalpana 1 data are available on one of the ISRO data portal, that is MOSDAQ, and INSAT 3D data is also available on this particular web portal, and I'll show you the link at the end of this particular lecture from where you can get the data set to study the different weather phenomena, and also you can identify using the data set which particular event was corresponding to an extreme event. From geostationary meteorological satellite, we can utilize the imageries from the visible sensors, infrared sensors, and the water vapor sensors. So the visible channel of the satellite measures light using the same wavelength as the human eye. In other words, looking at a visible satellite picture is the same as if an astronaut took a photo of the clouds and sent it to you. Just look at this picture. The more brighter area actually shows the presence of the clouds. In visible sensor, the objects with the higher albedo. If you are given an imagery from the visible sensor, then the objects with higher albedo ability to reflect sunlight appear brighter on the satellite image. and objects with lower altitude appear dark on the satellite image. Visible sir is only available during the daytime. The picture to the right shows the west coast still has not seen sunrise yet, because the main source of the energy for visible sensor is the solar radiation. Therefore, visible sensors and the imageries are available only during the daytime. Now, good uses of visible includes visible sensors, thunderstorm features such as overshooting tops and anvil shadows. You can also identify snow cover based on their different albedos. Most importantly, towering cumulus or TCUs, fog, marine layer clouds, outflow boundaries from convection, hurricane features, especially anticyclonic flow aloft, fronts, lows, and other large-scale features, lake effect features, and cirrus streaks, jet stream features, etc. You can actually monitor using the visible sensor images. Now come to the next, infrared sensor. Infrared satellite measure radiation output from the Earth into space. We can consider Earth as a black body, and as per the Wien's displacement law, the maximum of the emitted radiation lies in the 10 micrometer range. And this particular energy, which is emitted by the Earth's surface, that can be monitored by the infrared sensors, and based on the amount of this particular emitted emission from the Earth's surface, we can use this particular energy to derive different information about the certain meteorological phenomena or features. So infrared satellite measures radiation output from the Earth into space. In other words, it measures temperature, and one can infer clouds based on the different temperatures being measured. The colder an item is, such as a high cloud or a cold air mass, the brighter it is. The warmer an item is, such as a warm lake or clouds near the ground, the darker it is. Often color enhancement are added to the picture to aid in interpreting. This will often allow the user to see more detail about any of the developing weather feature. The user should compare the colors to the color bar or the key to determine the temperature of the clouds, and the cloud top temperature are usually given in Kelvin. And if you find cloud top very cold, then you could infer that the cloud is a growing cloud, convection is also forming, and you would have precipitation out of this colder cloud. And the higher the cloud, the colder it is, but beware, very cold air mass or a new snowpack can mislead you. So for this purpose, you should not use satellite imagery only for one time step. You should have sequential remote sensing imageries to look at the features and differentiate between the snowpacks and the clouds. Because if you just use the imageries for 6 or 7 time steps, you would find that snow will remain stagnant at one place, it will not move, and clouds will be moving. And also you can monitor whether the clouds are growing or are decaying clouds. If the clouds are growing and it's moving in a particular direction, then you could actually do the nowcasting using this particular information from the satellite image about the weather of a particular place. Now the good uses of IR include nighttime satellite use, because it actually uses the energy emitted from the Earth's surface. Strength, weakness often, especially MCCs and MCZ activity, approach of cold air masses. You can also monitor the dry lines during the afternoon. The cyclone development also can be monitored using the infrared sensor imageries. Troughs and ridges within the jet streams can be monitored using the infrared sensor, and the hurricane strength and the further analysis may be carried out using the infrared sensor imageries. Now the water vapor sensors. Water vapor satellite measures radiation output just as infrared imagery does, but at a different wavelength. Typically this wavelength is of the order of 6 micrometer, because water vapor has an absorption band in 6 micrometer range. So if you are given a sensor in 6 micrometer range, that is the water vapor sensor, and these imagery may be used for the monitoring of the water vapor content in the atmosphere. Brighter areas on the images represent greater areas of moisture in the mid and upper level of the atmosphere. Darker areas represent drier areas of moisture in the mid and upper levels. Very cold air can also show up fairly bright, just as in infrared imagery. Now the good uses of water vapor channel. Excellent for large scale features such as long wave tows, ridges, lows, etc. Dry intrusions within a cyclone. Large scale moisture port may be monitored using the water vapor sensors. Vertical motions. Areas of subsidence and rising air may be monitored using the water vapor imageries. Nicely developed shortwave tows and ridges also may be monitored using this particular sensor. So using 3 different channels, we can actually see the development of different weather phenomena. And if you are given the sequential satellite imageries, that can be used to see whether a particular weather phenomenon is developing or decaying. You can also see the speed of the propagation of such events. If there is a cloud formation, you can actually see by which speed these clouds are moving. If you are given the rain bands, you can actually see whether the intensity of the rain bands is increasing or not, and in which direction these bands are propagating. So in some sense, you can use these imageries for the nowcasting of certain weather events. As I said in the slide where I have shown you different geostationary meteorological satellite, I told you that these data are available on ISRO data portal. This data portal is MOSDAQ, and from this particular data portal, different data sets from different geostationary satellite are available, and this particular figure is from the Kalpana 1 QPE. QPE is the quantity precipitation estimation, and data is available for a fairly good time period. Likewise, from the Kalpana satellite, the upper tropospheric humidity is also available, and QP is the quantitative precipitation estimation, and the radiation corresponding to different channels is also available, and these are the other parameters which you can obtain from MOSDAQ portal. Those are atmos motion vector winds, outgoing long wave radiation, upper tropospheric humidity, rainfall, and sea surface temperature. This is another figure for the special distribution of quantitative precipitation estimation, QPE. This particular figure is for UTH, the upper tropospheric humidity. This is given in percentage. This imagery is from water vapor channel, and here is the cloud motion winds. So before we start the study on the extreme events using the satellite data, first of all we should focus on this particular study which was carried out in 2006. This study was based on the rain gauge measurements. In India, Indian Meteorology Department actually maintained rain gauges over the entire Indian region, and based on these rain gauges, certain data set has been developed. So one of the data set was used by Goswami et al., and they have published their finding about the extreme events over Indian subcontinent in in journal Science. It was published in 2006. So as I said, the data which was used for this particular study was from rain gauges, and the data they had used it for 50 years, starting from 1951 to 2000. For doing any analysis, you need to have a homogeneous region where you can carry out some statistical analysis. This particular figure shows the monsoon season rainfall over Indian region, and you would see that Western Ghats and the Northeast India are the region where we receive maximum rainfall during the summer monsoon season. Summer monsoon season starts from June and ends at September, so it's a 4 months long season. In 4 months long season, the maximum precipitation is being received by Western Ghats in the northeast India, and then central India receive moderate rainfall. Rajasthan region receive very less rainfall. Likewise, the Jammu Kashmir is also receiving very less rainfall. Here is the region of rain shadow, where hardly we get a good amount of rainfall, especially here. And Tamil Nadu receives rainfall in the winter season, not in the summer monsoon season. So overall, if we just look at this picture and take the average over entire Indian subcontinent, we would get average of the order of 8 millimeter or 7 millimeter per day. So if we just look at this rectangular box and take the average over this box, we would find a value that will be of the order of 7 to 8 millimeter per day. So in that sense, we can say this particular figure is a representative of rainfall of all India. And also, if we just see this figure, this particular rectangular box, the region within this particular rectangular box shows that there is not much variation, or in some sense this particular region is homogeneous if we consider rainfall. Therefore, the authors of this paper have taken this particular region for their study of the extreme events. First of all, they have shown the long-term trend of JJS rainfall. This green curve is the fluctuation in the amount of the total monsoonal rainfall. If we see the figure, we don't see any trend. There is no significant trend in this particular time series. What we can see in this figure is that over the 50 years of time period, the monsoon season rainfall is more or less stable. But if we just look at the standard deviation over the last 50 years of period, what we do see, there is an increasing trend. And this trend is actually significant, which was reported by Goswami et al. This trend was significant at 5% significant level. From these two figures, we can infer that on an average, the monsoon season rainfall is not changing, but the standard deviation, which is actually calculated over the 122 days time period of a season for a year, is showing an increasing trend. And it is possible only when you have certain spells of high amount of rainfall per year. You can have more standard deviation for a time series when you have some numbers like 1, 2, 3, 4 and a number of the order of 50 and 100. Means kind of sudden jump. And if you are given a data set like 1, 2, 3, 4, again 1, 2, 3, 4, 5, 6, this kind of time series will give you less standard deviation as compared to the time series I discussed just before of it. Means if you are given a data 1, 2, 3, then 50 and 100. Okay, so in this sense you will get more standard deviation, and actually that is happening with the Indian summer monsoon rainfall over this central region. And the authors of this try to show that from their study that however the total amount of the rainfall is stable over the last 50 years of period, but there certain amount of the high intense rainfall is increasing. That's why the standard deviation over the last 50 years of period is also increasing. They also try to show that the event which are greater than 100 millimeter per day is also showing an increasing trend, and the rainfall events which are in the range of 5 to 100 millimeter per day, they have considered these event 5 to 100 millimeter per day as the moderate rainfall, and the events which are greater than 100 millimeter per day, they have considered them as an event. So if we just look at the last 50 time series of these number of events which are plotted over the y-axis, the red curve is for the moderate rainfall events, for the extreme events, and the blue curve is for the moderate rainfall event. What do you see? You see a decreasing trend here. I mean the rainfall events where the intensity is less than 100, those are actually decreasing over the last 50 years of period. And the events which are corresponding to high intensity, means greater than 100 millimeter per day, those events are increasing over the last 50 years of period. And this particular curve, this shows the number of events which is greater than 150 millimeter per day. And this is also showing an increasing trend over the last 50 years of period. So through this study, Goswami et al. Proposed that over the last 50 years of period, the number of events which are greater than 100 or 150 millimeter per day are showing an increasing trend. And through this paper, the Goswami et al. Reported that in the coming years, we would expect an increase in the extreme rainfall events over the central Indian region of the Indian subcontinent. So this study was based on the ground-based measurement. These kind of study may be carried out using the satellite data as well. One of the study was carried out for the Western Ghats of India, and the data which was utilized for this particular study was the TRMM 3B42 version 7 dataset. TRMM is the satellite launched by NASA and JAXA. NASA is the Space Agency of America, JAXA is the Space Agency of Japan. It was a joint venture of these two countries, and the dataset from TRMM is available from 1998 to 2014 September. Now another version of TRMM has been launched recently, that is GPM, but for this study I am showing you this curve which is based on the TRMM 3B42 version 7 dataset. So what do you see here? This is the histogram. As we discussed in the very second slide of this presentation, that if you are given a long-term data set and if you plot the histogram from that data set, you can actually identify the threshold of the extreme event. The amount of the rainfall which can be considered as an extreme can be seen from this particular histogram. So here you see that maximum number of events are in the range of 0 to 100 millimeter per day. And if I zoom it further, you would find maximum number of events within 0 to 10 millimeter per day range. And as you go for the higher intensity, the number of events are decreasing. I have zoomed this figure further, and you do see that there are about 250 events are there which are corresponding to 300 millimeter per day intensity. So we can say that 300 millimeter per day kind of events the Western Ghats has experienced at least at 250 instances. This could be happen at the same place, or this particular event may be spatially distributed over the entire study region. That can be seen through a spatial distribution of these events. So what has been done further? Now, one method is to see the histogram, the other method is to define an extreme event using the percentile method. Percentile method is the method which gives you information about the percentage of the events which are lying to the left of a particular threshold. So using that particular percentile method, what we have now that if we take 99.95 percentile of the rainfall, the extreme events threshold will be of the order of 150 millimeter for the Western Ghats. So here just see the first figure. This figure is for the spatial distribution of seasonal rainfall over Western Ghats. The Maharashtra region, here is Karnataka and then Kerala. The spatial distribution of seasonal rainfall shows that the maximum amount of the seasonal rainfall is being observed over Karnataka region, and after that Maharashtra experienced high amount of rainfall, Kerala experienced relatively lesser rainfall, relatively lesser seasonal rainfall in the monsoon season. So this is the distribution for the entire monsoon. It is just giving you the intensity which is being averaged over the 16 years of time period for the 122 days time. And for the extreme events, what is being shown in this figure is actually showing the number of events when the intensity of rainfall was greater than 150 millimeter. So these color pixel, these are showing the numbers over the last 16 years of time period over Western Ghats. So what we do see here, even though the seasonal rainfall was more in the Karnataka region, but the extreme events which are considered whenever the intensity was more than 150 millimeter, those events are more for the coastal Maharashtra as compared to the coastal Karnataka. And you would hardly see any event, there are very less number of events in the Kerala region. Since the dataset has been used for the 16 years, and then you can actually give the probability, means the occurrence of this particular events per year. I have used a dataset of 16 years, and here you could see this particular red color. This is about 46. So for 16 years, at least 46 times, this particular place has received an extreme event. Therefore, the probability of the occurrence of this particular event, which is in the range of 150 millimeter, is at least 3 per year. Likewise, for the other places also, this probability may be estimated, and therefore this kind of information, this special distribution of extreme rainfall events is very crucial for the people who are policy makers. If they are doing any infrastructure activities or any other thing, this kind of information may be utilized for the policymaker for the better hazard management. Likewise, one more study was carried out over Northwest Himalayan region using the same satellite dataset. Here also we have utilized the TRM3B42V7 dataset for last 16 years, and this study has been carried out over Northwest Himalayan region. For this particular region, what we do see, the first figure is actually the elevation map. For every 25 kilometer, the elevation of the mountains have been plotted. Since we know this is the region where we get a mountainous belt. Maximum elevation up to 7,000 meter, means about 7 kilometer. And here you do see at this particular belt, the green color is the lesser elevation area. And as we go in this direction, the elevation is increasing. In the Jammu Kashmir region, we have maximum elevated mountains, and this belt is further narrow in Himachal Pradesh and much narrower in the Uttarakhand region. In this study, we also tried to relate the extreme events with the elevation of these mountains. And here is the mean monsoonal rainfall distribution over this particular region from the dataset. So what we do see, we have taken 3 states here, Uttarakhand, Himachal Pradesh and Jammu Kashmir. During the summer monsoon season, the maximum amount of the rainfall is being received in Uttarakhand, then in Himachal Pradesh, and there are many regions in Jammu Kashmir which may be considered as a rain shadow region. Only good amount of the rainfall is being received in this particular part. Here are many places in the region which are being received about 12 millimeter per day rainfall throughout the monsoon season. And as we go up, means as the elevation of the mountains increases, as the height of the mountain increases, the amount of the rainfall is also decreasing. Means we do see a inverse relationship here with the elevation. And if we just take the average over this state, the amount of the rainfall is more for the Uttarakhand as compared to the Himachal Pradesh. Now using this particular statistical distribution or the histogram curve, we again have defined some threshold for this mountainous region. So here one thing to be understand, that is, you should understand one thing, the threshold of the extreme events, that is the function of the geographical location of a certain places. Likewise, in the study which was given by Goswami et al., they had used 100 millimeter per day as a threshold, but for the Western Ghats we have taken 150 millimeter per day. And for this particular region, the Northwest Himalayan region, we have considered certain percentile of this particular distribution. So in this curve, if we do see that as the intensity of the rainfall increases, the number of events corresponding to these events decreases. So this particular range may be considered as a threshold for the extreme events. Now if we just take the 98th percentile, 98th percentile means the 98% of the data lies to the left of this particular threshold. Means only 2% of the events or 2% time you would experience this kind of rainfall over this particular region. So what we do see here, there are number of events are being shown in the color bar in different colors over this region. For the 98th percentile, the more number of extremes we do see in the Uttarakhand region, that is about 70 to 100. Lesser number of events in the Himachal Pradesh region and much lesser in the Jammu Kashmir region. Likewise, if we take another percentile, 99 percentile, so 99 percentile, you will have lesser number of events for this particular threshold, but the intensity will be more. Since you are taking this threshold where 99% data lies to the left of this particular threshold and only 1% data are lying to the right side of this particular threshold. So what do you see here? There are certain locations which are receiving this amount of rainfall about 100 times over the last 16 years of time period. Means there are certain locations where you are getting at least 5 to 6 extreme rainfall events which are in the range of 99 percentile. Further to this, we also have calculated 99.99 percentile. This particular threshold may be considered as a threshold for the cloudburst event because the intensity of the events will be much higher. So we just look at this intensity for 99.99 percentile, that will be in the range of 200 to 270 millimeter per day. And this particular intensity is actually changing from grid to grid. And you do see that this 99.99 percentile intensity is more in the Himachal Pradesh region as compared to the Uttarakhand region. So this figure was for the intensity corresponding to different percentile for each grid of the Northwest Himalayan region. And as we go for the second figure, so that I have not covered here, not included here, we can actually see the number of events corresponding to these intensity. And our analysis shows that most number of extreme events which are corresponding to 99.99 and 99 are actually occur in Uttarakhand region, that too also in the lower elevation regions. And then you would see certain extreme events in Himachal Pradesh, and Jammu Kashmir receives lesser amount and lesser number of the extreme rainfall events. So till now we have seen the study from the ground-based measurements, which were the IMD dataset. Then we have seen one study which was from the other satellite dataset, that was TRM3B42V7. So if you are given a dataset for longer time series, that time series may be utilized to define a threshold for a particular region. Then a post-mortem study of extreme events may be carried out. And if you are given the satellite imageries, you can actually monitor the different weather phenomena, and you can actually see whether the clouds are developing or decaying clouds, or in which direction the clouds are moving. Now I am going to show you another study which was actually carried out using the IMSRA rainfall dataset. This figure is for the cloudburst event at Leh, which occurred in August 5, 2010. In this particular event, 1,000 people have died, and it was further updated also later on. And Leh town, which is actually in the rain shadow region of Jammu Kashmir, experienced 250 millimeter per hour rain, means 250 millimeter in 1 hour. So it was a rare event for the Leh region. If you just look at this particular figure, the position of Leh is somewhere here, and the mean monsoonal rainfall is in the range of 1 to 2 millimeter per day, But on the day of cloudburst, this particular region received 250 millimeter of rainfall in 1 hour. So therefore it was an extreme event, and this event actually has been monitored using the IMSRA data. IMSRA data is the rain product which is developed using the INSAT 3A measurements. This data is also available on MOSDEC, that is the ISRO meteorological portal. And this figure is plotted for August 5, 2010. The cloudburst was reported on August 5 and August 6 midnight. So we just look at the rain pattern for August 5, 3 GMT. What we do see, that there was no rain in the Leh region in the morning time of August 5, but there was a strong rainfall in the central Indian region. Since the images are available for every 3 hours, so we can actually see the propagation or the movement of these rain bands over the 3-hour time period. What we do see here, the rain band which was actually over the central Indian region at 3 GMT, it was further intensified and expanded in the spatial or horizon direction, and also we do see different rain bands are developing over the Nepal region. After 3 hours from this particular event, we do see that the rainfall bands or the rain bands which were over the Nepal region are actually growing especially, and the intensity is also increasing with time. And even this time also we don't see any rainfall in the Leh region. After 3 hours from this time, we do see that the rain bands are actually again extending their spatial extension. The intensity is decreasing, but the rain bands are propagating in the northwest direction. At 3 GMT, we do see that now the rainfall actually, the rain bands, they are shrinking, the spatial extension has decreased, intensity has increased, and now this band from the Nepal region is entering in the Indian region. It further progressed towards the Leh region before 3 hours, and after 3 hours of, this was the portion at 15 GMT, means 3 PM. After 3 PM, at 6 PM, the rain band actually further intensified and going towards the northwest direction within the Indian boundaries. And after 3 hours of this particular instance, this is the actually location of Leh region, where you do see the maximum amount of the rainfall. This time is 21 GMT, means roughly midnight of as per the Indian Standard Time. And this time actually was reported by India Meteorological Department that this was the time when the cloudburst occurred in Leh region. So what we did see through these sequential images of rainfall, that for every 3 hours, the rainfall intensity was increasing. In between, extension of the rain bands increased and then further decreased, and these rain bands entered in the Indian region, moved towards the Leh region. Firstly, they formed over the Nepal region, moved in the northwest direction with a speed of 1 degree per hour, and the rain band also intensified for 3 millimeter in per hour. So this was the speed of the rain bands and the intensification of the rain bands. Therefore, by utilizing the satellite imageries, we actually monitor variation of the rain bands. However, this study was a post-mortem study, but if the satellite imageries, at least the visible channel or the infrared channels are available and we monitor them in time, then the nowcasting of such extreme events is also possible. So right after the Leh event means the cloudburst occurred 21 GMT, but after 3 hours of that particular event, the clouds from the Leh region dissipated, the intensity of the rain bands also decreased, and the bands further entered in the Pakistan region. So what we do see here, the extreme event is a very localized phenomena. or the cloudburst is a localized phenomenon, especially which is very small but the intensity is very high. And these kind of event, due to their ferocious activities, the rain gauges may not measure them. So satellite are the only means to measure these kind of extreme events. Just look at this picture. After 6 hours of this particular event, there is no cloud at all in the surrounding region of the Leh, and the rain bands is completely entered in the Pakistan region. Likewise, another study was carried out for the Kedarnath. The Kedarnath disaster of 2013, when the extreme rainfall event occurred at the Kedarnath town, and this actually was not as much localized phenomena as it was in the time of Leh event, but still the intensity of the rain bands on their location, the rain bands propagation, their direction may be monitored using this satellite data set. This data set is the TRM3B42 data set, and for different time period the rain bands have been plotted. This cloudburst event was repeated in the evening of 16th June. This particular figure is for 16th June. The color bar is showing the intensity of the rainfall and the position and intensity of the rain bands prior and after the Kedarnath cloudburst event is being shown in this particular figure. The maps are plotted for every 3-hour temporal resolution. The color bar indicates the rainfall intensity in millimeter per hour. The location of Kedarnath town is shown as white rectangle in the figure. So we do see here that prior the cloudburst event, the certain amount of the rain bearing clouds were present there. We do see some amount of rainfall was there, but at the time of the cloudburst, these rain bands actually intensified, and we do also see there was other streams of the rain bands which were coming from the Bay of Bengal and the Rajasthan region. These two branches actually merged over the Kedarnath region. Therefore, we did find a high intense rainfall during this event. Likewise, VHRR images for the monitoring of the cyclone, its progression, its propagation may be monitored over a certain time period. So through this image we would see that how this cyclone is forming and moving through the Bay of Bengal region and entering in the Bangladesh region. So these are the sequential images. Just see that how these cloud bands. This is a cyclone and this dark spot is the eye of the cyclone. As time progresses, since the sequential images are available from VHRR, we can see that the cyclone is actually intensifying and moving in the northwest direction, and now it actually has entered in the land region and actually hit the Bangladesh. So till now we have discussed the usability of the satellite data sets, and as I told during the presentation that there is a ISRO meteorological data portal from where the different satellite images and the data sets and the rainfall product, the cloud product, etc. may be downloaded, and this information may be useful for you. You just need to create your username, and through the administrative permission you will just fill up the form, and if the permission is granted, you can access these data sets and can do your analysis for the extreme events or for other weather phenomena. Likewise, the data are also available over the India Meteorological Department data portal. Here also you can order data set and get the different data sets for your studies.